VLPSos here. This is a video lesson for Python programming. Pixel matrix. This code is started with stub1. I have my code file in a folder on my computer, and in that folder I also have the palette code file which I import into my program. The palette file is giving me a dictionary of colors that I'll be using in this program. I also have two subfolders for resources, images and sound effects. Won't be using any sound effects in this code, but in the images folder, I have two graphics, two graphic image files. I'm going to import one of these in this code. When we create the screen with the setMode function, we are creating a pixel matrix. A matrix is an arrangement of rows and columns. A pixel matrix is an arrangement of rows and columns of pixels. Pixels are single points of light. When we use many of them, we can use them to create graphics. The screen is a pixel matrix. We could call it the primary screen because there's one pixel matrix, one surface that when we update, the user is going to see. We typically use the variable screen to mean that primary surface that everything eventually is drawn to and then updated for the user to see. When we create other surfaces, we are creating other pixel matrices of any size to make use of, and we've seen that in previous lessons. When we load a picture, we are also creating a surface. We're creating an additional pixel matrix every time we load a graphic, and the pixel matrix that we load then doesn't start as black. That matrix is the size of the picture that's loaded, and it starts with the image as the colors in the image as the colors of the pixels on the surface. That's done all at the same time every time we use the load function for a graphic. I'm going to uncomment these lines that have been part of the stub. I'm going to load a picture. I first need to get the path, the location of the folder and the subfolder that the image is in. I've done that with the path is equal to os.getCwd, current working directory. So that variable is used here. The value of that string is the path. I also need to, well, it's the path of the code file that I'm working on now. But to get to the location of the image, I also need to put in the subdirectory images. Then the file name and the file type. The file name for the image that we're going to use is sosmom 640 by or x 480. The dimensions of the image are given right in the title. This is very helpful for people that are providing images for programmers to import. So 640 width and 480 height is also going to be the size of the surface that gets created when I load this image and assign it to be the variable picture. So picture is a surface with that image on it. We can see, if we go to our frame loop, what got loaded and what that surface looks like. On the compose screen, I'm going to blit the picture surface onto the screen surface with the line screen.blit. Blit is the function. It's working on the screen, so we're blitting to the screen. What we're going to blit is the picture. That was the variable that we assigned the image that we loaded. And then the second part of this argument is where we are going to blit it. In this case, we're going to blit the picture's top left corner to the screen's top left corner. The top left corner has coordinates 0, 0, like the origin on an algebraic graph. I'm going to save and run right away. I'm in the habit of when I load resources, sound or images, I immediately check to see if there's an error. There often is, and some adjustments would need to be made, often in the string that represents the file name and location. Here we see that there wasn't an error. We do have a screen. The size of the image is not, or the dimensions of the image are not the same as the dimensions of the screen. I can see that the image is more narrow and higher or longer than the screen. But I can see that the image got loaded. And we viewed it. The next thing that we're going to do is we're going to take some time to make a well-organized display. We're going to use the image, but we're going to do something a little more sophisticated. I have as a hand-drawn note an idea of what we're going to go for. Imagining that this piece of paper is the screen surface. It's the dimensions of the screen. And inside are two other surfaces that are going to be created. We're going to call these frames. There's going to be two of them. And the frames are going to be sized and placed on the screen in such a way that we get a nice border on the top and the bottom and the sides and in between of two frames that are exactly the same size and centered this way. So we're going to do some work in organizing the creating the surfaces and the coordinates and the dimensions of these so that we can make a display like this for the user. The first thing to do is to choose the size of the border. It'll be 15 pixels. There's going to be a border on the left and right, top and bottom, and in between, and we assign it to be a variable. We're also going to then create or find or decide the dimensions, if I could spell it right, of the picture frame. There are two dimensions, width and height. I'm going to create variables for them. Before I create the surfaces. So the picture frame width and the picture frame height are going to be the width and the height of what I'm calling the frame that I'm going to make two of and then put on the screen. The picture frame width is going to be based on the screen width. I know the screen width. I have a variable literally called screen_width. So I need to think and do some math. What is the frame width if I want to take the screen width, account for 3 border amounts, and then have 2 of those frame widths placed in that space? How do I get the value of 1 frame width if I know the screen width and the borders? Here's how that math is going to work out. I'm going to take the screen width and I'm going to subtract 3 times the border variable. I'm going to put this in parentheses. Mathematically it's unnecessary, but it helps to visualize. So I have the screen width, but I'm subtracting 3 border amounts. What's left over are the 2 frame widths. So to get one of them, I need to divide by 2. I'm going to put this in parentheses because all of this is being divided by 2. Division creates a float, and we can't use floats or fractions of pixels to mean dimensions of surfaces. So I'm going to turn all of this into an integer with the integer function. This guarantees me now, no matter what the screen width or the border is, I can change the screen width and the border. The picture frame width will automatically be calculated correctly and represented as an integer. Picture frame height is going to be similar. What I'm looking for is the size of this dimension here. It's going to be based on the screen height. So the screen height, if I take away 2 borders, will leave the picture frame border, or the picture frame height. So the picture frame height is going to be a similar calculation. I could borrow this. I'm going to turn it into an integer, but it's going to be the screen height, and I'm going to subtract only 2 borders, and I'm not dividing it by 2 because I don't have 2 of them, I just have 1. I've got the picture frame width and height. I could create what I could call the picture frame size, because these are going to be surfaces that I'm about to make. I could use the width and height in the creation of the picture frame, or I could have a separate variable be the size. That'll be the tuple of 2. The width comes first, and the height second. Now that I have the picture frame size, I'm ready to make the surfaces. I'm going to make 2. I'm going to call frame_1, and it will be a call to pygame.surface to make an instance of the surface class, and then the argument is the dimensions. I just prepared the picture frame size to be the dimension. My variable picture frame size is a tuple of 2. It's exactly what I need to be the dimensions of the surface I'm creating. I'm going to make 2 of these. So I'm going to copy and paste and change it to 2, but it's going to be the same size. I now have 2 frame surfaces. I'm going to fill one of them. I'm going to fill frame number 2 with a color so that I can see it distinguished from the rest of the screen and the other surface. And my colors come from palette. In this case, I'm going to use the color dark gray. I'm now going to consider, I've got the surfaces, one is filled dark gray. I'm now going to consider where they need to be blitted onto my screen. So this piece of paper, again, is notes to help me visualize what I need to work out and the math that is involved. The top left corner of the surface is going to be blitted to somewhere on the screen. The top left corner of the screen is over here in the top in the corner. So the corner of the surface, the first one that I'm going to blit, doesn't line up. I'm going to blit the first frame a border width over and a border width down. That'll be the blit point of the first frame. The second frame is going to have its top left corner blitted at a different location on the screen. So where is that location? I take the origin of the screen surface and I'm going to go over by a border, a frame width, and then another border horizontally. And then I'm going to go down by a single border to get to that top left corner where I'm going to put that second frame. So I'm going to work out the coordinates first in the place where I create my variables in constants, and I'm going to call 1 frame 1 blit point. And I use my notes to work this out, and I remember that the blit point for frame 1 is simply going to be border to the right and a border amount down. The frame 2 blit point is a little bit more sophisticated. Recalling from my notes, it's going to be 2 borders, so 2 times that border value, plus a frame width to the right. And then a border amount down, so I don't modify this. I have just done the work to create my surfaces, my blit points of them on the screen. I can now compose the screen. So instead of blitting the picture, I'm blitting each frame. Frame_1, but not at the origin, at the blit point that I created, which I called frame 1 blit point. And I'm going to blit another thing to the screen, so I'm going to copy that. It's going to be frame 2 blit point. Let's see if this all worked out. So what I see is I see the screen and it's filled with black. I see one rectangle of color, that is the frame 2 surface that was filled with dark gray. I don't see the frame 1 surface. It's there, I assume, but it also is filled with black because black is what a surface is filled with by default. What I'm going to do with the first frame is I'm going to put the picture on it, the image that I loaded. I'm going to, under the comment draw objects, I'm going to prepare the frame 1 by blitting the picture to it. And just to see what I get when I blit top left corner to top left corner, that means the blit location of the picture onto the frame 1 is going to be at 0, 0. Let's see what I get. So in my frame loop, we're checking. I'm going to first blit the picture onto the frame and then the frame onto the screen. So I ought to be able to see it. And I do, but the picture is larger than the frame or the surface that I'm blitting it to. So that doesn't give me a good piece of the picture to use. I want to get more of the middle of the picture onto the frame. So how do I do that? I'm going to change the blit point of the picture. But I want to show by model what I'm doing because this is something that's very common to do. I have a model piece of paper that's going to stand for my frame, and it's smaller than the graphic image surface that I want to put to it. If I line up the top left corners as I just did, then I'm looking at only the portion of the picture that I can see by the dimensions of the surface that it's blitted to when I line up the top left corners. And the portion that I see, I can't expand that without modifying my actual picture graphic. But I could center the picture graphic so that the screen gets those pixels that are more in the center of the picture. So how do I do that? I change the blit point. So how? The top left corner is what goes on the surface's coordinates. So if I wanted to move the picture, the green, so that the part of the screen that shows the picture is going to be more centralized, then I need to move that blit point up. Moving up means that I need to blit at a negative y location. Positive y goes down, so going up is a negative y. And if I also go to the left, in the negative x direction, then I'll move that blit point, the point of the top left corner relative to the 0, 0 coordinate or origin of the surface that it's blitting to. So the coordinate of this point relative to this origin is going to be to the left, meaning a negative x, and up, meaning some negative y. Blitting at negative coordinates is often the way to center or adjust a picture. So I'm going to choose to blit at negative 200. That'll move the picture horizontally, and negative 50. That'll move it vertically. Let's see what I got. I can now see more of the center of the picture. And it has a well-organized display on the screen of my two frames with borders around it and a border in between. These frames are the same size, they have the same dimensions. The next thing I'm going to do is I'm going to use this second frame to correspond to the first frame and scan through the pixels of the image one at a time and do something on the second frame based on what I see on the first. A little complicated to say, but what I mean to do is to create nested for loops, which means a for loop inside of a for loop. The first one will be for row in the range from 0 to the picture frame height. What I'm doing with this for loop is I'm iterating through a range of integers. I'm iterating through as many integers as there are pixels in the height of the picture frame. So this for loop is iterating once per pixel in the height. And if I put another for loop inside this is nested for loops, and call the iterating variable column in the range from 0 to the picture frame width, then for every pixel on the height, we can think of it as for every row in the picture, I'm also going to iterate through every single pixel in the width of the picture, or I could think of that as once for every column of pixels. Then every time I iterate through these two loops, I'm going to visit the location of every single pixel in that surface graphic. So this column here, this code block, is going to be done once for every location of every pixel, and the location will be the column row that I'm currently processing. So what do I want to do at every single pixel in the surface? I'm going to do a few things, but the first thing I'm going to do is I'm going to draw circles at every location. I'm going to, well, let's take advantage of the stub and remind us that the stub includes some very helpful notes, like drawing of a circle. If I post that note there, then the argument is descriptive. Where do I want to draw it? I want to draw it to the frame 1. What color from palette? How about blue? Where am I going to draw a small circle? At every location of the pixel. And locations of the pixels are the iterating variables of these nested for loops, column row. We'll draw a small circle of radius 5, and it will be aligned with the 4, nearly filled in. I'm also going to draw a circle on the second frame, simply by changing where I'm drawing the circle, and we'll also change the color. Let's see what we got. 2 rectangles of solid color. What happened? I thought it was going to be a circle. Well, sure, but what we see is we see the evidence of a circle, even though it's small, drawn at every single pixel location. So after all of that has been done and we displayed at the very end, we can see that it has been filled up with circles, solid color, after it's finished. Something that we could do in order to get an understanding of the processing is to not update the display when this is all finished, but update it while it's processing. While it's processing in this sense means while we're in the for loops. So we're going to make a comment called view changes. And what we mean by view changes is to simply update the graphics display more often, once every time we iterate. But if we're going to see these changes, we also need to compose the screen so that we see it when we update. So we're copying the blitz of frame 1 to the screen so that we can see the screen when it gets updated after it draws these circles every single time. Let's see what we got now. Well, we see how we're getting, in the end, 2 rectangles of solid color. What's being done is we are seeing the processing of those circles being drawn. It doesn't look like circles because what we're seeing is we're seeing the bottom edge of the circle that is being drawn and advancing the color that we could see the history of before. So it's iterating many times very quickly, once for each pixel. That's why it's drawing it slowly. we can improve the understanding of this processing by not seeing the history of all the other circles drawn, but maybe just the current one. If we're going to do that, then before we draw, we need to prepare those surfaces as they were when they started. So what does it mean to begin again or fresh with the second frame? We filled it with dark gray. So we're going to do that again at the beginning of every iteration. And what does it mean for frame 1 to start? It means that we're putting the graphic on it. So what we're including now is we're starting our surfaces over as if they were fresh from the beginning. One's a graphic, the other is dark gray. We're drawing circles to them, and then we're seeing the change immediately. And we're going to do all of that every single time we iterate, and we're iterating for every pixel in the surface. What we see here is the correspondence between the circle that is being drawn, on each frame. The correspondence of position. It's happening at the same position on the surface at the same time. And we can see that it's still taking a long time to process because we're doing it once every pixel. Eventually it will scan both surfaces all the way to the bottom. We're not going to wait to finish. But what we have just coded is we have coded a way to visit every pixel on one surface that has a graphic and visit the same location on another surface that we could do anything we want to. So rather than draw circles on each one, we're going to take the pixel color on the graphic and put that very same pixel color on the gray surface. I'm going to comment this out. And we're going to start a new comment for what we mean to find the pixel color on frame 1 and place the color on frame 2. How do we do that? Well, we're going to get a color on the surface. So we're going to create a variable called color, and it's going to be assigned to be on frame 1 a call to the get_at function. And what we're getting is we're getting the color, and we need to provide the location of where that color is at. And the location is our iterating variables column row. So every time we iterate, at every location of every pixel, we're going to get at, which means at that location, get the color, and assign it to be the variable color. What are we going to do with that color? We're going to, on frame 2, use the function set_at. We're going to set that color at that location. What's the location? Well, same column row that we got the color at on the other surface. And what are we going to set? We are going to set the value of color. Let's see what happens. The camera might not be picking up that there is a track of a pixel and the color is being set, but we still have our image gray because we're still starting over with the fresh graphic and the fresh fill of gray every frame. In this case, we want to see the history of all of the previous iterations of this happening, not just one pixel at a time. So we take away these 2 lines of code that started over. And we're going to see this process and the history of the previous iterations recreate the graphic, pixel by pixel, simply by scanning the graphic on the first frame, getting the color at every location, and putting that color on the second frame at the exact same location. We're duplicating. And it takes a while to process. we could speed up this process by not seeing it every single time we iterate. The update process takes time. Another reason why we don't want to update all of the time. We want to code in such a way that eventually we only update once at the end of every frame and not in the middle. Updating more than once per frame kind of messes up a lot of math of sophisticated programs that involve time. So we don't want to update every single frame. We can see this another effect by dedenting. I highlighted and pressed Control open bracket in order to move all of those over so that this process of updating is happening only once every time we iterate our first loop, not every time we iterate both. So what happens and what changes that going to make? We can observe that very quickly, but not instantaneously, the graphic was reproduced. And what we saw was the evidence was updated every row. After the entire row was duplicated, we only saw one row at a time, not every pixel at a time. And of course, this was just fun. This updating every row or every pixel was fun to see, but not something that we would want to continue in a regular program. So we're going to see the update only at the very end. And how long is it going to take? It is nearly instantaneous. The human eye could barely track that there was any processing done at all. The process of updating is very time consuming, but it's not very time consuming to scan all of those pixels and put those colors on the other frame. It was done very quickly. We also have a nice formatted display here. Last thing to talk about, and to possibly include, is that this process was done inside the while loop. We did this inside the while loop so that we could see our program do one pixel at a time. But that was just for the purposes of this lesson. If our intention was to duplicate a graphic using our code, then we probably wouldn't want to do it in the frame loop, because then we would be doing it every single frame. And if we're simply preparing a graphic that we're only going to need to prepare once, then we should do all of that work before we start our frame loop. So it's only done once, and then it's used later on in our program repetitively. Now we can get around this, the fact that we are doing this every single frame, by, even though it's in the frame, we could move it out. But if we don't want to move it out, we could put it behind a Boolean. In other words, we could put it behind the condition of being done. If done is equal to false, then do all this work to prepare the graphic, which is duplicating the graphic. If done is true, then it no longer does this process. So if we only want it to be done once, then we put it on condition of done being false, I'll need a double equals, and then immediately turning it to be true. This is a clever way of doing something only once, even though it's in the frame loop, which by design does things repetitively. And of course, we have to include initial value for this Boolean and set done equal to false so it gets done at least that once. Let's see if this works. What did I do? Oh, didn't make a condition, so we put it behind an if. Now what's happened is the duplication of one surface onto another has only been done once. My frame loop is still processing, so if I had other parts of this program, they would be able to be run or executed much more quickly because I'm not doing the duplication every single frame. Now you have seen evidence that a surface is just a pixel matrix of colors. You have seen how to use the getAt function to find the color at a location on a surface and setAt to place a color on a surface, and how these functions were used to copy an image. Experiment with altering the color tuple between getting and setting to alter the color of the entire image. You can use this lesson code file as a stub, but you must get your own image to work with. Remember, if the values in a color tuple are less than 0 or greater than 255, it will break your program. So you must ensure that this does not happen while altering the color tuple values. To be clear, this process is duplicating. The nested for loop, so the sophisticated way of visiting every pixel, but the duplication itself is very simple. We just get the color at one and then immediately set it at another. But here is what you can do in between those two steps. When you get the color from one surface, you can modify it before you set it at the other. If you modify it the same way every single time, then the entire image will receive a modification that was based on the first. Tinting is the very easiest thing to do, like increase the red value of every single pixel. But then comes the warning. If you're increasing the values of pixels, you got to make sure that after the increase there is no pixel that has a color value greater than 255 or less than 0. Or else you'll break your program and it won't work. Have fun.